AP Chemistry, how are we doing today? So today we're going to be covering molecular polarity. All right. So for this, you are going to need to make sure you've got your notes. You're going to need to make sure you've got something to write with, and then you will also need a periodic table. Okay. So let's kind of dive on into molecular polarity. So first off, what is the meaning? Okay. Well, if we talk about a substance being polar, so if I say that a molecular substance is said to be polar, we say that if the molecule is polar. Okay, well, you're like, okay, well, duh, that makes sense, right? Okay, yes, that does make sense. But what does polar actually mean? Well, polar means you've got one end that is positive and one end that is negative. Okay, so I've got a positive side of the molecule and a negative side of the molecule. Now, I could have multiple positives and one negative, but I still end up having a positive and a negative side. I kind of think about it, if I take a piece of paper and I cut it in half in any direction that I choose, if in one of those directions one side is positive and one side is negative, that is a polar molecule. Okay? Now, if we're talking about polarity, we've already talked about polar, but we also have to keep in mind nonpolar. Nonpolar means that there is no pole, meaning there's no positive and negative on the sides. Now, there could be positive on all the sides or negative on all the sides, but that's still a nonpolar molecule, because to be polar, you have to have one side positive and one side negative. Okay, so let's actually look at this. So first off, ways to end up nonpolar versus ways to end up polar. Okay, this is really just here to kind of help you sort through when something's going to be polar and when something's going to be nonpolar. First off, nonpolar. You immediately know if a molecule is nonpolar if none of the bonds in it are polar bonds. Okay, and you're like, well, how do I know if it's a polar bond or not? Well, polar bonds have to do with electronegativity. That's, if you think back when we talked about ionic versus covalent, we talked about those differences in electronegativity. We talked about how we form an ionic bond, and it's ionic if its electronegativity difference is greater than 1.69. If it's a polar bond, it's between 0.4 and 1.69. And if it's a nonpolar bond, it's between 0 and 0.39. Okay, so those are all things that we've kind of talked about already, but just kind of a reminder, this is something that is recurring, so you got to keep it in your mind. All right, so nonpolar bonds, if I have no polar bonds in the molecule anywhere, then the molecule is immediately a nonpolar molecule. Okay, now if I do have two polar bonds or more, but all of those bonds are the same all the way around, then it is again nonpolar. So if everything on the outside is a positive charge, or everything on the outside is a negative charge, that molecule is a nonpolar molecule. Okay. So how about ending up polar? Well, we end up polar if we have at least one polar bond and they don't completely cancel each other out. Okay. And so what we end up saying is that instead of everything on the outside being positive, we could have most things on the outside positive and one thing negative. Well, then they're not actually canceling out, right? I've got one side positive and one side negative. Okay. Now, this does kind of help walk you through. It's kind of like a flow chart for helping you recognize if something's polar. So let's go over it real quick. The first question you can ask is, are there any polar bonds in the molecule? If you say no, it's nonpolar. If it's yes, you kind of continue on. So yes, let's say yes. Yes, it's got a polar bond. Okay. The next question is, are all the atoms surrounding the center atom the same? If it's yes, then it's if it's yes, then the molecule is nonpolar. Now, why would it be nonpolar? Well, if everything on the outside is the same, that means everything on the outside has the same charge, positive or negative or whatever it is, and so they're all going to cancel out. If it's no, it is polar. All right, so if everything on the outside is not the same, then polar with some minor exceptions. Now, if you're interested in figuring out what those exceptions are, they are down here by this little asterisk. Okay, so moving on. So yes, I decided that yes, everything on the outside is the same. So the next question I have to ask is, are there any lone pairs? Now, remember, lone pairs, based off of what you learned about Vesper shapes, lone pairs repulse everything else, right? So they're going to push away everything else. And when they do that, they change the shape. So normally I would say, yes, this is a nonpolar molecule because everything on the outside is the same. Okay? But when I add that lone pair, all of a sudden that shape is going to change, and we can start to reveal some positive or negatives that weren't there originally. And so, is there a lone pair on the central atom? If no, it has to be nonpolar, right? Because that means all of that same atom are on the outside, and everything on the outside has the same charge, right? If yes, we continue on. It asks, is the molecular geometry square, planar, or linear? If not, it's polar. If it is, then it's nonpolar. All right. So that's just kind of a flow chart to kind of help you along with that, to help you kind of recognize if something is polar or non-polar. But when I come down to it, when it comes down to me figuring out if a molecule is polar or non-polar, I like to draw its shape. I have found that that helps me visualize it a little bit better. Okay. Now remember that with your molecules, even with a non-polar bond, if those electronegativities are not perfectly the same, there is going to be some slight attraction to one side over the other. And so when we're keeping that, it's sometimes hard to kind of think about it. Okay, well, this is a non-polar molecule, but it looks like there might be some polarity there because it's pulling in one direction over the other because its electronegativities aren't the exact same. And so just keep in mind that kind of range that I was telling you. If it's between 0 and 0.39, it's nonpolar. 0.4 to 1.69, it's a polar covalent. And then from 1.7 basically up, we're talking about an ionic bond. Now, a couple things to take note of. A lot of times a common misconception is that when I'm talking about a polar bond, I'm talking about it being charged. No, that's not the same thing. Remember, charge refers to ions. Charge refers to I've got a gaining or losing of electrons, all right? And when we're talking about molecules, we're not talking about gaining or losing of electrons. We're just talking about an unequal sharing of those electrons, okay? Ionic bonds are also neither polar or nonpolar because they're not molecules, right? If they're an ionic bond, they're not a polar bond or a nonpolar bond. But I will say this. A lot of times when we're talking about this and we're talking about is that polar or nonpolar, sometimes we will refer to an ionic bond as quote unquote polar because it does have that positive and negative side that's on it, okay? But do keep in mind that when we form an ionic compound, they're naturally going to be neutrally charged, right? Because when those two things combine together, they're canceling out each other's charge, right? The positive from the metal and the negative from the non-metal, those are going to cancel out, which is why we need different amounts of different metals and non-metals. Now, one last thing to quickly talk about is that really, in my opinion, if I'm talking about a polyatomic ion, it doesn't really make any sense to think about it as polar or nonpolar, right? Because again, polyatomic ions are covalent compounds, right? And so it doesn't really make sense to think about them as polar or nonpolar because overall, that charge that they have, that positive or negative charge because of them being a polyatomic ion is going to take precedent. It's going to dominate everything else that is there, be it the molecule is all polar or the molecule is all nonpolar. That charge that we have is going to dominate it. And so we typically just say that a polyatomic ion is charged. We don't typically ask, is it polar or nonpolar? Now, you might see that in some of your practices, but again, that's just kind of helping you figure out how would this molecule look? Is it polar or nonpolar? Okay? All right. So in the grand scheme of things, your bottom line is polarity is basically a property of either bonds or molecules. And it is not a meaningful property for ions or ionic compounds. Okay? So we're talking about molecules and molecular bonds, covalent bonds. We're trying to figure out only with a covalent bond, that unequal sharing or that equal sharing of those electrons, what's going on there. Okay? All right. So here's what we are going to do. Now, first off, you are going to need to make sure you're drawing your Lewis structure for each of these. I am going to actually draw the Lewis structure in this small box here that is the number of polar bonds. Now, you do probably need to have a separate piece of paper for this because it will just give you some more space to work with. All right, so I have AsCl3 over here. Now, I'm looking at this and I'm trying to figure out, okay, well, first off, how many polar bonds are there? Well, to do that, I do need to draw the shape, the Lewis structure for this. And then I do also need to make sure I've got my Vesper shape because that helps me visualize what's going on. Does it have a positive and negative end? Okay, so number of polar bonds. All right, so I have As, it's bonded to 3 Cls, and they have to fill their outer octets. Okay, now I do look at that, and then I also have a lone pair here in the center. Okay, now if I were to take this and redraw it to reflect that Vesper shape, what we're going to end up with is the arsenic with 3 chlorines coming off of it, and then there is that lone pair. All right, now I need to look at their differences in electronegativity. So if you don't have a table of electronegativities given to you, you are going to have to use your general trend that we told you on the periodic table. So starting at fluorine, every time you move down, your electronegativity decreases by 1. And every time you move left, your electronegativity decreases by 0.5. Now, that is a generalized trend. It's not perfect. And if you were given an electronegativity table, you would see that it's obviously wrong in a lot of places. But it is a good way to help you kind of get a generalized idea of what their electronegativity should be. Okay, so I start off at arsenic. Well, arsenic is 2 down from fluorine and 2 left from fluorine. Okay, so the electronegativity of fluorine is 4. So if I go 2 down from fluorine, 1, 2, okay, and then I go 2 left, I'm left with a total of 1 in terms of my electronegativity. So the electronegativity of arsenic is about 1. Okay, then I need to look at my chlorine. Chlorine has an electronegativity of, well, chlorine is down 1 from fluorine, and that's it. So fluorine is 4. I went down 1 to chlorine, so it's 3. So arsenic has an electronegativity of about 1. Chlorine has an electronegativity of about 3. So my differences in electronegativity is really about 2. A very big difference in electronegativity. Okay? So looking at this, if I know that, what that tells me is that there is going to be polar bonds that happen here, right? So this chlorine is going to have a higher electronegativity. Well, remember, electrons move towards that electronegativity, right? So we're going to move, let me actually change my color here. We're going to move in this direction towards the chlorine with those electrons, right? So what that does is we've got a slightly negative side here, and we've got a slightly positive side there. Okay, we're going to do that same thing with all of those chlorines. Slightly positive, slightly negative. Coming in this direction, we got slightly positive and slightly negative. All right, now if I look at my molecule here, how many polar bonds do I have? Well, I've got the one that's here on this chlorine, the one that's on this chlorine, and the one that's on this chlorine. So I have a total of 3 polar bonds attached to this arsenic. So there are 3 polar bonds. The next question is, how many nonpolar bonds are there? Okay, nonpolar bonds. Well, if we look at this, all of our bonds here are polar. So there are 0 nonpolar bonds. Does it resonate? Okay, so thinking back at our rules on resonance, Remember, resonance means I have a bond that could have moved in a different place. So looking back at my arsenic here, there's no bond that could be placed in a different area, right? This is the same as this, and it's the same as this. So all of those bonds are the same. So no, there's nothing that's going to resonate. So is this molecule polar? So looking back at this molecule, I have my bottom half here is negative, and my top half is positive. So do I have a polar molecule? Yes, I do, right? I've got one side positive and one side negative. So is it polar? Yes. Okay. How do I know? Well, I know because chlorine to arsenic is a polar bond. Since that's a polar bond, normally this would be a non-polar molecule, right? If I had those chlorines spread out around it with no lone pairs, this would be a non-polar molecule. Why? Because everything on the outside would be negative. However, when I added that lone pair changed my shape, and now I've got one end that's positive and one end that's negative. Okay? So what I want y'all to do is I want y'all to pause your video and actually solve this next problem. All right, so go ahead and pause your video, solve this next problem, and then we will quickly draw it and go over it. Okay, hopefully y'all pause your video. So now let's actually take a look at this and get working through this H2S. So first off, the Vesper shape or Lewis structure here is going to look like this, okay, with two sets of lone pairs on that central atom, okay? When I did this, I found that my electronegativity for sulfur is about 2.5, and for hydrogen is about 2. So thinking about that, since I know that there is a 0.4 difference, that tells me that that is a polar bond. So that tells me that the electrons are actually going to move towards the higher electronegativity, so towards sulfur, and away from our hydrogen. So the hydrogen side is slightly positive, and the sulfur side is slightly negative. Are there any polar bonds? Yes, there are 2 polar bonds. There are 0 nonpolar bonds. This does not resonate. And then, is it a polar molecule? Yes, it is. Okay? All right, y'all. So that is polarity. Please let us know if you've got any questions. I will end up finishing the rest of this table for you, so you can find that on your key posted online. All right. Again, let us know if y'all have any questions. Hopefully y'all have a great rest of the day. Bye, y'all.